So this is our continuation of volume by rotation. We did the disk method. If you haven't watched the disk method video, by the way, go watch that first. Now we're going to do the washer method. So to use the washer method, what's going to happen is your cross sections are going to look like a washer. And by washer, I mean this shape in front of you. It's something you might see in a toolbox. We actually use them a lot in physics also. But it's basically a circular thing with a hole cut out in the middle of it. So it's a disc with a hole in it. So go ahead, pause the video. I want you to see if you can find the formula for the area of that. Okay, so the area of this is going to be, first of all, our outer area is pi uppercase R squared. But you have to take away the inner part. So it's going to be minus pi lowercase r squared. And we actually write that as pi times uppercase r squared minus lowercase r squared. And we're going to use this in our formula. So you can think about this as a cross section, and we still are going to use the formula for a cylinder, which is pi r squared h. The h is still going to be our dx. So our formula here is going to be the integral from a to b of pi times my overall radius is going to be big R squared. I'm going to write it as R of x minus little r squared times dx. This one's a little bit longer. There's a little bit going on. So you might be asking, well, how do I know if I'm using the washer method or the disk method? Basically, you're going to use the washer method if there is space between your shaded region and the axis of rotation. So let's go ahead and do an example. So you might notice that the problem for the washer method is quite a bit more complicated than the disk method. That tends to be the case. For now, feel free to use your calculator to evaluate all of your integrals. Usually if you get these on the AP exam, it's either a calculator question or you just are asked to set it up. You don't actually have to solve most of the time. So first step is to draw a picture. Go ahead, pause the video, and please draw the graph. So this right here is my shaded area. I know the graph is not perfect, but I hope you got something similar to this. Before you can write any integrals, you will need to find your intersection points. That's usually the second step on these. Once you have a graph, you're going to want to figure out where they intersect. And remember, we do that by setting these two equations equal to each other. And this one's thankfully something that's factorable, so it's not too terrible. So you're going to find that the intersection points are at x equals -2 and x equals +1. You're welcome to go back and find the y values that go along with these. You just find them by substituting it into the equation there. There's also a very good chance that you'll get a problem like this that has non-nice intersection points that you're going to have to figure out on your calculator. Just remember, if you do that, you're only going to really pay attention to the x values, unless you're integrating in terms of y, but we're not going to do that yet. All right, so now that we have our intersection points, I first want to show you what this actually looks like when you rotate it. So I'm hoping you can kind of see what's going on based on this picture. I did try to keep the colors the same. The line being rotated around the x-axis is that red part. The parabola being rotated is that blue part. It does kind of look like a what we call a truncated cone, which means a cone that has no top with a vase cut out of it. So it's like the blue part is the vase and then the red part is the cone. I do want to mention that if you were to cut a cross section out of it, so now you would have that line would be this outer circle, and then on the inside from each cross section you would have another circle cut out. And there would be part of it that was solid. It would kind of correspond to that shaded area that we have there. So it would look like a washer. That's why we call this the washer method, because it's a circle with a hole cut out of it. So let's go ahead and write our equation. So I'll just rewrite the equation that we had. It is the integral from a to b of pi, I'm just going to pull the pi out front, times big R squared minus little r squared times dx. So my big R squared is this, by the way, the x-axis is the axis of rotation. So my big R squared is going to be the distance from the outer radius, which is this line, to the x-axis. Thankfully, in this one, we're only rotating around the x-axis, so it's just going to be 0 below, but that doesn't always happen. We'll do one at some point that is going to be rotated around another line. So my big R, my large radius, is going to be equal to the equation of that line, which is negative x plus 3. My little r is, my small radius is going to be the distance between that parabola and the x-axis, the axis of rotation, and that's my little r of x, which is going to be x squared plus 1. So this integral is going to be pi times the integral of negative x plus 3 squared minus x squared plus 1 squared times dx from my leftmost x, which we found was negative 2, to my rightmost x, which we found was positive 1. This is my integral here. Now, these types of problems, I think I mentioned before, they're really complicated. Definitely use your calculator for these. You're not going to be asked to solve this on the AP exam by hand. They don't do things like that make you take a lot of time. Most of the time, you'll just get a problem where you have to set it up. But if you solve it on your calculator, you should hopefully get 73.513.